All right, so we've talked about the graphs of sine and cosine. So let's do the other four. Let's do tangent. Now, for sine and cosine, we did the whole plotting points thing, right, to get the graph. I'm not going to do the whole plotting points thing here to get these graphs. I'm going to use the fact that we can write the other four in terms of sine and cosine to be able to, here's a review sheet too, to be able to get the graphs of the tangent and the cotangent and so on. So in terms of sines and cosines, how can we rewrite tangent? Sine over cosine, right? So what I'm interested here is in kind of important points, if you will, for the tangent graph, and then figure out what the graph has to look like as a basic shape, and then maybe add a couple of extra points on here. But really, I'm just trying to get the basic shape here to start with. Okay? So in particular, some of the kind of the important points that you like to talk about as far as graphs go are the intercepts. Where do they cross the axes? Well, how do you find y-intercept? What do you do to find the y-intercept? You set it equal to 0? You make the x equal to 0, right? You plug in 0 for x, right? When we do plug in 0 for x, if I want tangent of 0, well, again, if I think about it in terms of sines and cosines, that sine is 0 over cosine is 0. What is sine of 0 equal to? Yeah, sine of 0 is 0, right? And cosine of 0 is 1.
Where
right?
exactly does those values come from? On the 0 and the 1?
Yeah, you can think about the graph. Yeah, the graph will probably be the easiest way to do that. Because remember, sine, if you think about the sine graph, if I think about where the y-axis is kind of the starting line, the sine graph starts at 0, 0, and then the cosine graph starts at 0, 1. Okay. All right. So that would be the y-intercept. And then how do you find x-intercepts if you wanted to do those? What do you do? Yeah, you set the function equal to 0, right? Right? That's how we do x-intercepts, is you set the y equal to 0 and solve for x. Now, I'm not as interested in solving for x as I am thinking about the properties here. Tangent, again, is equal to what? The sine over the cosine. So what we're really interested in is where is a fraction equal to 0, right? Because I've got sine over cosine. So how do you tell if a fraction is equal to 0? Do you look at the top or do you look at the bottom? The top, right? The top is what tells you if it's equal to 0. Do we know when the sine's equal to 0? Do we know the x-intercepts for the sine function? What are the x-intercepts for the sine function?
0 pi over 6 pi over.
Is it pi over 2?
0 pi and 2 pi.
Okay, so yeah, it's pi
2 pi.
and 2 pi and negative pi and negative 2. It's all the multiples of pi, right? Remember those? Right? So it crosses the x-axis at those values. Right? So the x-intercepts for the tangent function are the same as the x-intercepts for the sine function, because again, if you think about it as a fraction is 0 and the top is 0. Right? Okay? All right, well, so that gives us at least some points on the graph, right? Well, let's think about some other properties. All right, so you've dealt with functions that are fractions before. You dealt with rational functions. If you had college algebra, you definitely dealt with rational functions. What's the root word of rational? Ratio. Okay, what is it a ratio of? What's a rational function a ratio of? what kind of functions are on top and bottom if you have a rational function. Starts with a P. Polynomials, yeah, the top and bottom are polynomials, right, for rational functions. But when you did rational functions, there were some things that you were interested in for rational functions, and one of those things was, where does it have issues? Where is it undefined? How do you determine if a rational function was undefined? What did you do? You set the denominator equal to 0, right? We have the same kind of problem here with tangent, don't we? Because tangent is defined as a fraction, right? So where would the tangent function be undefined?
On the in the sense where cos x equals 0.
Okay.
So pi 2, 3 pi 2.
So right, so we're going to set the denominator equal to 0. So it's at when the cosine is 0, and that happens at the pi over 2, the 3 pi over 2, 5 pi over 2, right? All those odd multiples of pi over 2, correct? Right? Now, thinking back again to your rational function ideas, what typically happened on the graph when you had a 0 on the denominator? What kind of a thing did you get on the graph typically when you had a 0 in the denominator? A vertical asymptote, right? And that's exactly what's going to happen here. We're going to get a whole bunch of vertical asymptotes. So we're going to see these vertical asymptotes at all these odd multiples of pi over 2. All right, so now it's a matter of trying to fill in the gaps. So let's see if we can fill in this middle gap here first, just this part that's around the y-axis. Okay, so this is from 0 to pi over 2. Think about those as angles. If you're going from 0 to pi over 2, what quadrant are you in? If you're thinking about these as angles, from 0 to pi over 2, what quadrant would those angles be in? Quadrant 1, right? Is tangent positive or negative in quadrant 1? Positive, right? So if I'm going to draw the graph of tangent, am I going to draw it above the x-axis or below the x-axis? Above. I'm going to draw it up here, right? And I have to get close to this asymptote, so it has to look like that, right? It has to be positive because the angles that I'm plugging in are in the first quadrant, and I know I have to get close to that asymptote. Okay? Let's think about the other side over here. We're between negative pi over 2 and 0. If I think about those as angles, what quadrant are we in? Quadrant 4, right? Because we would have gone down below the x-axis as opposed to above. Quadrant 4 is tangent positive or negative? Negative. So I have to be down here and again get close to that asymptote. So that's what that piece of the graph looks like. Right? Almost looks like an x cubed function, kind of. Right? It's not quite x cubed because we have asymptotes, and x cubed doesn't have any asymptotes at all. Right? But the kind of that S shape idea. Okay. All right, let's see if we can fill in the rest of this. Same idea over here. Pi over 2 to pi. If we think about these as angles, what quadrant? Quadrant 2. Tangent positive or negative? Negative, right? So it'll be down this way. Pi to 3 pi over 2. What quadrant?
That's quadrant 3.
That's quadrant 3, and tangent is positive. So flip that way. And notice that those pieces here are going to look exactly the same. The graphs will look exactly the same. And so hopefully now you can see that they start to repeat. So the next piece will look like this. piece over here will look like this, and so on. No, run off the screen, but that's the idea. So this is our graph for tangent. So just to write down some properties for tangent here, we have, well, our domain. If I write it as interval notation, it's a little bit goofy, but I'll do it anyway. It'll be, we know we have a negative pi over 2 to pi over 2 that are not included, right? And then I have to, that happens every n pi. We have those chunks. That's all I'm representing there. Okay. What's its range? Yeah, it goes as down as far as you'd ever want and up as far as you'd ever want because of those vertical asymptotes, right? We have X-intercepts. Those were the multiples of pi, right? Just like sine. How about its period here? So the negative pi over 2 is this one, right? And then pi over 2 would be this one. All the n pi is doing is just saying shift it. Shift it. That's all the n pi part means, is that we have them every interval there. It's just saying that there's a domain issue every time we hit an odd multiple of pi over 2. Don't get too caught up in that notation. Just remember that at the pi over 2's it has asymptotes. That's all we're really saying. How about the period? How long does it take for this graph to repeat? Does it take a whole 2 pi to start repeating? No, what is it? It's just an interval of pi, right? So that's a difference between tangent and sine and cosine. Besides the fact that we've got asymptotes, we've got the period is different. And then just to write down the vertical asymptotes, just so that we have those. The equations are x equals pi over 2 plus multiples of pi. That was a weird noise. Doesn't know where it came from. All right. Are we okay with how we got the graph? And again, the big things that you're going to need to remember about the graph for tangent are, where does it cross the x-axis, those x-intercepts? Where does it have asymptotes? Okay, those are the kind of the big ones. Another one that pops up a bit is kind of a point that's on here. If we put in pi over 4, just to mention another specific point that's on there, what is tangent of pi over 4? It's 1, right? Because sine and cosine are equal, right? So you would have that point at 1, just as another reference point if you needed it. I'm only mentioning it because sometimes you need it as a reference point, but I'm not going to worry about the other ones, for at least for the graphical purposes. We okay with that? All right, well, let's flip over, pun intended, let's flip over to cotangent. In terms of sine and cosine, what's cotangent equal to? Cosine x over sine x, good. So, thinking about this in the same way as we thought about tangent, okay? Okay, so let's think about zeros and think about asymptotes. Which of the two functions, cosine or sine, would we worry about for where it crosses the x-axis? Which of the two functions would we worry about? Cosine, because why?
Because it's on top.
Because it's on top, right? So if we're looking for x-intercepts again, we look for where the top is equal to 0. Right?
Yep.
Yeah? Okay? So when is cosine equal to 0?
Power 2, power 2.
Okay. Yeah, so the odd multiples of pi over 2, right? The pi over 2, the 3 pi over 2, negative pi over 2, negative 3 pi over 2. We agree? Okay. What about where we're going to get those asymptotes? Where is this function going to have problems? Where is the... So what's the two functions are we interested in? The sine, right? Because again, the sine is on the bottom in this case, right? So when is sine equal to 0? Okay, so pi, 2 pi, negative pi, negative 2 pi, anywhere else? The y-axis, right? We got one here too, don't we? Where the 0? We agree? Okay. Now let's just play connect the dots like we did in the previous one. Here's 0 to 2 pi. 0 to 2 pi, right? Is angles again what quadrant? Quadrant 1. So are we positive or are we negative? Positive, right? So I'm going to draw it above the x-axis and get close to that asymptote. So I have to go this way. Am I going to the left? Well, you can think about it going this way, but the arrow is just representing that it's getting closer and closer to that line. How about from pi over 2 to pi? What quadrant would the angles be in? Quadrant 2, right? Yeah? Net positive or negative in quadrant 2? Negative. So we're going to go down towards that asymptote. So it looks like the tangent function flipped upside down, doesn't it? Okay. Pi to 3 pi over 2? It's going to be positive again, right? Because tangent's positive and cotangent is the reciprocal. So it's like this. Do you agree? Okay. And then quadrant 4 will be negative, and then we just get those same pieces over and over and over again. So there's what our cotangent graph looks like. One of the things that we didn't write down for tangent and won't write down for any of the other three that are left was the amplitude. Why don't we talk about amplitude for tangent or cotangent? It would just be infinity, right? It's going off to infinity in both directions, isn't it? Okay, so asymptote doesn't make, or excuse me, amplitude doesn't make any sense here. All right, but we can write down the same kind of things here. Our domain, this one is a little bit different. We do n pi to n plus 1 pi for the domain. Again, this is just talking about where the asymptotes pop up. Range again is what? Okay. And our x-intercepts are those odd multiples of pi over 2. Right? And they're all pi in away from each other. So it's pi over 2 plus n pi. What about the period here? Because the y coordinate of any x-intercept is 0. So I'm just writing the y coordinate in. What is the period? It's just pi again, right? Because it takes that 0 to pi or pi to 2 pi interval to draw the graph. And then it starts to repeat. And there's asymptote at 0 and pi and 2 pi. So our asymptotes are the multiples of pi. Again, what I'm most interested in about these particular graphs are these important features. Where does it cross the x-axis? What's its period? What are its asymptotes? So that we have an idea of what the shape of it looks like. We're interested in the basic shapes here, at least especially at this point, because we'll need to use this stuff later as far as the shapes go. Any questions about tangent or cotangent? We okay with these? Yeah, maybe. Yes. The domain? So remember, n can be any integer. All this is saying is that if I put in 0 for n for n, I would go from 0 to pi. So that's here to here. Right? If I put 0 in for n, that's 0. That's 1. So I get 0 to pi. No, that's not 0 to pi. So what this notation means is we can plug in any integer for n. Right? So this is just a quick way to write 0 to pi, or pi to 2 pi, or 2 pi to 3 pi, or negative pi to 0, or negative 2 pi. I didn't want to write out all of that, right? And it keeps on going forever, doesn't it? This is just a quick way to write this. So all I'm saying is that I can go from 0 pi to 1 pi, 1 pi to 2 pi, 2 pi to 3 pi, and so on up the line. This is just describing where the x's are that I can plug in. And in particular, since I have parentheses here, it's really telling me what x's I can't plug in. Notice that goes hand in hand here with the asymptotes. That's the idea. All I'm doing by writing that is just reiterating that the pi's, the multiples of pi's, are the bad points, the ones that I can't plug in, where we get those asymptotes. That's the big thing to remember, is that's where the asymptotes are. Any other questions on it? All right, so let's talk about the other two. It's stuff that's on Hawks, yeah. Yep. All right, so let's talk about the other two that we haven't done yet. Let's do secant. In terms of sines and cosines, what's secant? 1 over cosine. Okay, good. So, before I draw anything, is this graph ever going to cross the x-axis? No, because again, to cross the x-axis, we would set the function equal to 0, right? So we have a fraction that would equal 0. And a fraction is 0 when what is 0? To the top, right? The numerator is 0. Can the numerator ever be 0? No. So this will never cross the x-axis, ever. Okay? All right. So to help us get a graph of secant, I'm going to put in a helping graph here of the cosine graph. So I'm going to put it in red so that I know that it's different here. Now again, if we think of the y-axis as a starting line, where does the cosine graph start? If I think about the y-axis as a starting line, where does the cosine graph start? At 1, right? Up here? And then it hits pi over 2, 0, and then pi, negative 1, and then back up to 0 at 3 pi, and back up to 1 at 2 pi. Right? Okay, so the red graph here is cosine.
The one with the asymptotes.
Yeah, go ahead.
The asymptotes are pi over 2. 3 pi over 2.
Yeah, I agree. So this is where this pi over 2, the 3 pi over 2, the negative pi over 2, the negative 3 pi over 2 are where the cosine graph hits the x-axis, right? Where cosine is 0. What does that do here to your secant? It puts a 0 in the denominator, right? So that's where all those asymptotes are going to pop up. So we're going to get an asymptote at pi over 2, get an asymptote at 3 pi over 2, negative pi over 2, negative 3 pi over 2. Now let's get the shape of the graph. We're going to get a couple of helping points for that. What's the secant going to be here at 0? Well, cosine was equal to 1. So what's the secant going to equal if cosine is 1? 1, right? So it'll be right there. And then I have to get close to the asymptotes, right? Right? The graph has to get close to the asymptote. So I have to go this way and this way. How do I know it couldn't go down? What did we say it could not do? The graph does not do what? Doesn't hit the x-axis at all, right? Right? I have to get the whole point of drawing in the asymptotes is so that you know that the graph gets close to the asymptotes, right? I can't go down because I would hit the x-axis. We know that it doesn't hit the x-axis at all, so it had to go up. It does kind of look like a parabola idea. Let's look over here. Yeah, so if cosine is -1, what does secant have to be? Also -1, right? Yeah, 1 over -1 is still -1. And again, we have to get close to both asymptotes, so we have to go downward. And then up here, it would be up again. So the black graph is the one that we're interested in. I only drew the red graph in as a help, right? So again, the big parts here, the asymptotes happen when cosine is 0, right? At those odd multiples of pi over 2 again. And then we have these, what look like U-shaped things, kind of alternating. So just to write these down again, I'm not going to bother writing the domain again. I don't want to be more confusing than apparently it already was. Let's look at the range. Notice the range is actually in 2 pieces, isn't it? What's one piece of your range? 1 to infinity. Do I include 1? Does it actually hit that point? Yep, sure does, right? So I would do a bracket 1 up to infinity. What's another piece? Yeah, this is where we do the union symbol. Yep.
Bracket -1 to -1.
And then write that in the other direction, right? So -1 and below, or 1 and above, right? That's our range. So we've got that gap in the middle. How about the period here? Pi, it's not pi, right? Because we got it flips, doesn't it? So this one actually takes actually 2 pi again, right? Because I don't actually hit the same thing. Notice that this u up here doesn't get repeated until over here again, right? So it's a 2 pi. And then again, just to write down the asymptotes. There'll be those odd multiples of pi over 2 again.
This
This will be on the next test. I'm just worried about sine and cosine for this one. For the graph. This one okay? So the last one we need to do is cosecant. In terms of sines and cosines, what's cosecant equal to? 1 over sine, right? Reciprocal of sine. Okay. So again, is this ever going to equal 0? No. Same reason why, right? It's not going to equal 0 because the top is never 0 here. Again, let's get a helping graph with sine. For sine, if we think of the y-axis as our starting line, where does it start? If we think about the y-axis as a starting line, where does it start? 0, right? And then it goes up to 1, down to 0, down to -1, back up to 1. So we get this graph. Again, the red graph here is not part of the graph of cosecant. I'm only doing it to get as a help, right? Where is the cosecant going to have issues? Where is it going to be undefined in this case? Okay, so, yeah, so we had 0, pi, 2 pi, negative pi, negative 2 pi, and so on, right? This continues forever. And again, why is that where it has issues? This is where the sine is 0 and it makes the denominator 0, right? It's the whole reason why we know we can put those in there. How about these points up here? If the sine is equal to 1, what's cosecant equal to? 1 again, right? And am I going to make these get closer to the asymptote by going up or going down? If I go off of this one point here. It's going to be up again, right? Because again, what do we know about the graph? It can't cross the x-axis. Can't go down from there, can it? If we're down here at -1, which way is it going to go? Down. And then we have similar things on the other side. Looks a lot like the secant graph, doesn't it? Just shift it a little bit. Which is not a huge surprise because sine and cosine look the same. They're just shifted. Right? A little bit. Right? So, if we write down the properties for cosecant here, if I can get it to scroll. Let's do range again. Is the range any different than it was for secant? Nope. Oops. It's a bracket. That's not a negative. And what else did I do? Period. What's the period here? 2 pi. And those asymptotes again happen where? Yeah, the multiples of pi, you go to the n pi piece. Any questions about the cosecant one? Again, notice with cosecant we don't talk about amplitude or secant because again it's going off to infinity, right? So there's not a lot of point in talking about amplitude for those. Any questions on that? Okay. So those are the other 4 graphs. So let's talk a little bit about your test on Monday. Those 4 graphs, again, like I said, we'll put these graphs on the next test. I'm just worried about sine and cosine for this test.
As in just drawing them by themselves, or like having to like
You have to do the shifting too, yeah. Do the reshifting too. The ones just drawing by themselves are the ones without the calculator. The shifting ones, you have your calculator. Okay. All right, so as far as the test goes, you had the radian and degree conversion stuff, right? Being able to convert an angle from degrees to radians and vice versa. We did, what else? We did arc length. And this also had to do, we had some linear speed and angular speed that went along with this. So for arc length, remember your formula was, oops, I got that backwards. Arc length we denote with S, and it's radius times the angle. What's the important part with the theta? It has to be measured in radians, right? Your linear speed, I just refer to it as a velocity, a v. Remember, that's your arc length over time, or your radius times theta over t. How far did it travel per unit time? That's linear speed. So the arc length gives you how far it traveled. Out of this formula, which part is the angular speed? The theta over t, right? How much did it rotate per unit time? So the notation for that is an omega, but I'm not really worried about that part. It's the angle over time. And again, what do we want theta measured here? Radians, right? That is a really ugly looking radians written. All right, we also did area of a sector. And that formula was, I can write down the right letters, 1/2 r squared theta. R again is the radius, theta is measured in radians. Hey, look at that. So those were those beginning formulas that we talked about. We also talked about exact values for, I'll call them special angles. Oops. Okay. So remember, what I mean by this is if you have an example, if I wanted to do, say, cosine of negative 7 pi over 3. What's the reference angle? Pi over 3, right? So if I think about the triangle, pi over 3 is, what size? That's a 60, right? Okay. So the opposite side from the 60-degree angle is, that's the opposite side of the 30, right? It's square root of 3, right? Remember, the opposite side from the 60 is the one that has the root 3 in it. Okay? So if I want the cosine of that, if I want cosine of pi over 3, what do I have? That's sine, right? Cosine is the adjacent.
How did you get those?
How do I get those? Well, it's probably easier to remember them, but the whole point of it is where it comes from is if I take an equilateral triangle with a 60-degree angle here, and it has side length 2, if I drop down that perpendicular, what does it do to the other side? It splits it, makes it 1. It also splits this angle up here, right? And if you use Pythagorean theorem, you get square root of 3 here. That's where it comes from. All right, so I know that this is going to have a 1/2 in it, right? Because the reference angle is pi over 3, so it has to have a 1/2 in it. So the other piece I need to know is where did this end up? If I think about where does the angle end up, right? Okay, so if I start on the positive x-axis, which way am I going to rotate, up or down? Down. If I go all the way around, how far is that? That's negative 2 pi. How many pi over 3s is that? 6 pi over 3, right? So I got to go one more. So what quadrant did I end up in? 4? So will this be positive 1/2 or negative 1/2?
Positive.
Positive, yeah. So it's just 1/2. So if you did something like, say I asked for cotangent of 19 pi over 6, say. What's the reference angle? Pi over 6, right? Okay. So pi over 6 again is, in degrees, that's 30, right? Side opposite 30 is 1. We agree? So what gives you cotangent? It'd be the square root of 3 over 1, right? It's adjacent over hypotenuse. So I know it's going to be square root of 3. It's adjacent over hypotenuse, or adjacent over opposite. I said hypotenuse and wrote the right thing, but said the wrong thing, right? Adjacent over opposite. Now the last thing I need to check is it positive or is it negative, right? Okay. So again, where do we end up? All the way around is 2 pi, which is how many pi over 6s? 12, right? So I've got 7 more to go. Halfway around again is 6 pi over 6, right? So that's 18 of them. So I got to go one more. So what quadrant are we in? 3? So is it positive or negative? Positive. Yes?
Is the reference angle just pi over whatever the denominator is?
Yep. For radians, yeah, it's always pi over whatever the denominator is. For degrees, it's harder. You actually have to do some subtraction. But for radians, the reference angle is always pi over whatever the denominator is. As long as it's reduced. As long as the fraction's reduced. It's always that. Okay. So what else did we talk about? We did some right triangle applications. Oh, had a couple of those on the quiz. There's a couple on the review sheet. And then we also did graphing sine and cosine. And then we also did transformations of these functions. So we did amplitude, period, phase shift, and vertical shift. And again, we did some of those in class. There are a couple of those on your review sheet as well. So making sure you can identify those and doing the graphs of the transformed functions as well. Again, tangent, cotangent, secant, cosecant graphs will be on the next test. Just for graphing, just concentrate on sine and cosine for this test. Okay? Questions at all? Math Center will be open 4 to 10 on Sunday if you need to stop by and ask them anything about questions about studying. All right. Have a good one. We'll see you Monday.